Welcome to review for null space and nullity. We're going to and dimension, we want to just cover this again briefly so that you can see how it all wraps together. The whole idea of null space is we're used to x plus y equal to 5, 2x minus 3 equal to negative 8. And what we're used to is figuring out what values for x and y will make these true. Well, what it means is you're going 1, 1, 2, negative 3 times xy, and you're getting those equal to 5, 5, negative 8. So essentially what we're doing is we're finding the value for x that when I go x and y, xy equal to 1, 1, 2, negative 3 inverse, 5, negative 8, that those are solutions. And remember what a solution is. A solution is the value that if you set these equal, if you say x equals 3, a solution is what is x, so that if you subtract 3, you get 0. And so x minus 3 equals 0, or y minus 5 equals 0. This produces the answers to the solution, but it's essentially finding the values that when plugged in will make that 0. So what happens is in vectors, let's take this vector right here. If we break it down into reduced row echelon form, what happens is that we can augment it to set it equal to 0 like we did with x equal to 3 and y equal to 5. You can always say x minus 3 equals 0 and y minus 5 equals 0. So we augment this matrix in the reduced row echelon form so that we can find the solutions essentially that make it true. So when we do the augmented form, remember that you label these x1, x2, x3, x4, x5, and the answers are 0. The parts that are not connected to one's leading coefficients of 1 or leading ones, these are the ones that we assign to our unknown variables. So, for example, here you would call, I think they called x2, they called this r. So x2 equals r, x4 equals s, and x5 equals t. Okay? Because they don't have the ones. Okay? So then when I solve for x2 equals r, x4 equals s, x5 equals t, now we can express x1 in terms of xr, x2, x4, and x5 are r, s, and t. So x1 is going to be negative t. It's going to be a positive 3/2 s, and then it's going to be minus 2r. And that's what we have here for x1. And then x3 is going to be negative 2t and negative 3/2 s. But what's cool about this is that then what you do is you set these, I'll use the yellow here, you set these up so that now we can produce this nullity matrix or nullity vector sum. It's a vector combination for x1, x2, x3, x4, which becomes the solutions that we had talked about earlier. So for example, when we line these up, x1, x2, x3, x4, x5. Okay. We take a look at all of these, and we say, all right, x1 has an r in it. So we go r, s, and t. R has, for next one, a -2. S has a negative, is a positive, 3/2 and a -1. X2 only has an R in it, has no S and no T in it. X3 has a negative, has no R, a -3/2 S, and a -2T. And then for X4 has no R, 1 S, no T, and it has no R, no S, and 1 T. And so those are what we call the nullity, but it's the solution of the reduced row echelon form of your matrix that can help you find a solution set, the AX equals 0. This is what X is that can help us find it if we have constants R, S, and T. And that's pretty amazing because we don't have a 4x4 or a 5x5 matrix. We have a 3x5. So this is why it's so unique. Now when you take these three vectors, that's called the subspace spanned by it, and the number of them is called the nullity. So the null A is the linear combination of those. The subspace span would be just the list of those vectors in the RST workspace. Okay? And the nullity is how many of them there are. And I think that is helpful. The rank, of course, we had talked about that before. We defined the rank as the number of vectors here. You could also count it as the number of, let's see, I don't know if they have the rank here. Yes, so for that same one, we did the reduced row echelon form of it here, and then we were looking at the nullity and the span of it by doing that whole RST thing. If you just do the reduced row echelon form, these two are what make up your basis, or what we call the row space, because these are the two rows. Okay? And then when you look at the reduced row echelon form of this with the zeros and ones, okay, that's your column space. And they called it the basis was just the 1, 0, 0, 1, 0, and then the actual column space are from the original. That's what gives you the column space here. And they were saying that the row rank is equal to the row rank of A and the column space of A. And in this case, all of these are 2. So what you're doing is you're taking a matrix that doesn't give you an identity matrix. It gives you part of one. And then you can reduce row echelon for it. You can go back and do what we did here to find the nullity in terms of RS and T, which is good. That's super helpful for an answer. It's like x equals 3, x equals 5. But it's very limited when you have underspecified matrices. So that's how we deal with the underspecified matrices. And then when we do the reduced row echelon, we have this way of looking at it with the rank A, column rank, and row rank. Row rank are the actual rows that would give vectors of the reduced to 1 as the lead coefficient. And then the vertical of that without the other specifiers would be your column space. Now, there's a second method, and that is to do what they call a transposed matrix and then do a reduced row echelon. And that one's kind of cool too. So you take this thing we just had and transpose it. 1, 2, 1, 1, 3, 1, 2, 1, 1, 3, 2, 4, 0, negative 1, 2, and you transpose it, right? So in doing so, take that and do a reduced row echelon form for it using your calculator. And notice that everything down here goes to 0. But you still can see that, okay, these are going to be your basis, because those are the columns that match up to the elementary reduced row echelon 1, 0, 0, 1. Okay, and then I think this one goes further. Maybe not. But that's just another method, and you get the rank, the row rank. Remember Scooby-Doo? Row rank is equal to 2 again. So this is an alternative method, works great. And then I just want to finish up with this consistency check. So we want to see if a system is consistent. Consistent means is that there's a relationship between your values, your, I think it's the column spaces, and the answer 325. There's a connection between those. They're consistent. And there'll be actual values that we calculate. So we take this example, put it into a matrix A and a matrix B, just like what we did. And notice it's not going to be a nice square where x equals 3, y equals 2, and z equals 5, because you have three rows and 4 columns. And so there's going to be some unknowns in here, kind of your underspecified thing. So I take this and then I do the reduced row echelon form again and get this. We've got our old column spaces again, 1, 0, 0, 0, 1, 0. That's the basis. Then if you want and that's of R, if you want it of the original A, then you just say, okay, 1, 0, 0 here matches up with this one, 1, 2, 3. This 0, 1, 0 matches up with 1, 0, 1, which matches up to there. The basis for the column space of A is the same. Okay? I don't know why this is repeated. This must be a mistake. Wondering if this, yep, it's a duplicate. All right. So then we do what we want to do then is take the basis of A, these two, and do a linear combination with 3, 2, 5. Okay. So we did first thing we did was reduce row echelon of A. Then we found column space, basis of column space, and then we're going to solve. Now, how are we going to do that? Well, we're going to, well, I shouldn't say solve. We're going to do a linear combination. Linear combination. And then we're going to solve. Okay, so here goes. So you have 3, 2, 5 is equal to some constant times the first column space plus b times the second column space, which can be converted into a plus b equals 3. 2a is equal to 2. I'm just going across here, right? going across. So the last one's going to be 5. Well, 5 is equal to, I'm just going to do the 3a plus b is equal to 5. So a is equal to 1 here. You can see that using this. And then b is going to be, if this is 3 times 1, 5 minus 3 is 2. b is 2. 2 plus 1 is 3. So there you go. So those are your two values that will make b consistent. And so since they even exist, then consistent. Then ax equal to b is consistent. It has solutions. It has relationships. And that is the nullity taken to the end. I hope this helps. Take a look at the problems assigned and see if you can find the column space of A, the nullity of A, and the consistency of A. See if you can do that. That'll come up on the test. Oh, one more thing. I just caught this dimension and nullity formula. This is helpful in relating all of this. So if you take the row rank and the nullity, it should add up to how many columns there are. So if you, let's say you had this one here, and you see that there's four columns. Okay, we found a row rank equal to 2. So what do you think what do you think the nullity of A is if you know n is 4 and the rank A is 2? Well, the nullity, if you went through all that work, you'd find that that was 2 as well. So check that out too. There's a good example here. You'll be able to find those. One more video to watch, and that is the linear transformation video.